Now, we've talked about photons, and we want to emphasize the quantum or quantized nature of photons. So light is quantized. They're only available in discrete whole numbers of photons. And for example, you can have one photon. You can have two photons. And as we will see, you can have 6.022 times 10 to the 23rd photons. Which of course would be 1 mole of photons, as we'll see. So 1 photon, 2 photons, a mole of photons are all possible. But a half a photon is not possible. And so quantized basically means you can count them, you can quantify them using whole numbers. Now, things that are quantized in our regular life, or we can think of as being quantized, the typical example is stairs, and the stairs can be thought of, you can have one stair or two stairs, or one step or two steps, but what is a half a step when you're going up a set of stairs anyway? So other things that are quantized, you might think that letters are quantized because if you drew half a letter, it would not have any meaning. So atoms are quantized. You can't have half an atom. It becomes something different. So lots of things are actually quantized. And light, even though each photon is very small, as we're about to see in the next calculation, you can only have a discrete or quantized or whole number of them. And as we'll see in this calculation for B, for a 100-watt light bulb, that we have a lot of them even in light bulbs. So the question says, or the example says, a 100-watt light bulb radiates 100 joules per second if we assume that the wavelength of the light bulb is 525 nanometers only. And this is an approximation because light bulbs tend to give off all of the colors of the visible spectrum, well, depending upon what type of light bulb it is. But for the calculations point, we'll just do one wavelength. Then the question will then be how many photons are emitted each second? And this is a bread and butter or typical calculation that we will do, or two calculations. So we've already talked about how if you have a specific wavelength, you can find energy. So E equals H times frequency. And once you have that, and we have that C equals wavelength times frequency. Now, since we have wavelength, we're going to now solve this equation for solve it for frequency, and then plug in to the energy equation. So rearranging this equation, we have frequency equals c, the speed of light, over wavelength, and then plugging that into the energy equation, energy equals h, Planck's constant, times c over wavelength. So here's the equation we're going to use to relate the wavelength that we've been given to energy, and that will be for a single photon. And then we'll talk about this 100 joules per second. So let me come all the way back over here and use up all my space on this. So hc over wavelength, h is Planck's constant, 6.626, times 10 to the minus 34th joule seconds. C is the speed of light in a vacuum, or the speed of electromagnetic radiation. That's 3.00 times 10 to the 8th meters per second. Divided by my wavelength. My wavelength is in nanometers. And in this time, just to do something a little differently, I'm going to put in my 525 right into my equation. And then instead of writing nanometers, since 1 nanometer equals 1 times 10 to the minus 9th meters, I will just write times 10 to the minus 9th meters there. And so that's a shortcut method of doing my unit conversion. When I do this, I get that, so 6.626 times 10 to the negative 34th times 3.00 times 10 to the 8th divided by 525 exponent 9 minus, I get 3.79 times 10 to the minus 19 as the number. And we see that our meters cancel out and our seconds cancel out. So our units here are joules, or as we've already discussed, joules per photon. And now this joules per photon, what we'd like to do is we'd like to use it as a unit conversion factor. Let me show you how that works. I have 100 joules, and I know that there are 3.79 times 10 to the minus 19 joules per photon. So if I put my joules with the number on the bottom, 3.79 times 10 to the minus 19 joules per 1 photon, I can calculate how many photons there are to deliver or in each 100 joules. The only part we need is the 100 joules for this part, because it says how many photons are emitted each second. So we'll start just with our 100 joules. 100 divided by 3.79 times 10 to the minus 19. And I get that there are 2.64 times 10 to the 20th photons. And that is the number of photons that are emitted each second, a very large number of photons. However, remember, photons come in quantized numbers. You can count them, even if you've got to count very high into very large numbers to get to the actual numbers. And I will say that this number will turn out to be on the same general order of magnitude, although it's a little smaller in this example, as moles, so 10 to the 23rd. And we'll talk more about that later.